All right, I wanted to do a key for the online quiz for my OChem 1 students because I try to use quizzes as a study tool to kind of help check yourself so that you're more prepared for the exam. So makes sense to share the key for them. So the first question was describe how you would make the following into a Lewis structure. So because it's pretty hard to upload images during the exam or the quiz and make sure that everyone is like have the same fair opportunity, I felt like a good way to test your understanding would be to describe how you'd make the following into a Lewis structure. Oh, it wasn't NH3 though. It was CH3, CH2, CH3. And so the thing I would start with is by the first thing I'm going to do is I'm going to look at the periodic table. I would want you to write in full sentences, but I'm going to do shorthand since I'm not typing. I'm just writing by hand. Look at the periodic table. Identify the valence electrons. Now, you didn't have to actually say how many there were on there because I didn't provide a periodic table. I didn't count off if you didn't say how many, but carbon has 4 valence electrons. Hydrogen has 1. We have 3 carbons, so that's 12. And we have 3, 4, 5, 6, 7, 8 hydrogens. So that's 8. So there's 20. And I'm only doing that just so that you can see how I would do the problem and how I would go about writing it out. So the only thing that I would grade would be what words you wrote. So look at the periodic table, identify the valence electrons, add them all up. Then the next step is to make the initial structure. Of the Lewis structure with single bonds. And you have to identify the central atom normally, but in this case, you can use the clues, and a lot of you reference that in your answer, and that's totally fine. You can either do the central atom based on electronegativity, or because we have the condensed formula, we know that the carbons are going to be at the center and they're going to be surrounded by hydrogens. And then the next thing we're going to do is count to make sure we use the proper number of valence electrons and that everything has a full octet. So the thing here is a lot of you mentioned how that you would draw the putting the carbons in the middle, surrounding them by hydrogens. I'm not going to write it all out, but that's what I was looking for the second part. But you didn't talk about the valence electrons or the counting to make sure everything was there. So if you did describe the proper structure, but you didn't talk about counting up the octets and counting up the valence electrons, then I gave you 3 points. If you talked about either the octets or counting up the initial valence electrons, I gave you 4. And if you didn't, if you talked about both, then you got full points. And if there was like something nonsensical, depending on how much nonsense it was, I gave 1 or 2 points. So that's how I would do it. Just to check those, it looks like we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, because each bond is 2 electrons, so we have the right number of valence electrons. And this carbon has 4 around it, this carbon has 4 around it, this carbon has 4 bonds around it, so the right octets for all the carbons, and hydrogen can only have 1, so it's pretty, you can quickly check and see that that's right. So that's how I would have approached those. The next question, most people got this right. What is the hybridization? You look at the electron domains, and there's only 3 electron domains. This positive charge actually means that there's nothing else there. If you think about formal charge, carbon has 4 valence electrons minus 3 things bonded to it equals +1. So there's nothing else present. Some people mistakenly thought this positive charge was a 4th thing bonded, but there's only 3 things bonded here. So there's only 3 things bonded, then we need an S and 2 P's, so that is sp2 hybridized. The shape of anything sp2 hybridized is going to be trigonal planar. I gave you 1 point if you gave any correct shape. even if it wasn't the right one, just for knowing Vesper theory basics. But if you got the right shape, you got all points on there. So trigonal planar, they're all 120 degrees apart. That's like a flat structure. It's not like pyramidal or anything. So it's 120 degrees between these, but it's 180 degrees. It's hard to draw it, but like from this hydrogen to that hydrogen, like, or from this carbon to this hydrogen, it's from the side, it would look like hydrogen, carbon, hydrogen, sort of like a flat thing if this was like a piece of paper. I don't know. It's hard to draw on here, but hopefully y'all know. If not, you can look it up. Okay, so what is the intermolecular forces present between two HCl molecules, and describe those intermolecular forces? So what I was looking for, this question was 6 points. Dispersion forces are present in all. I don't know why I put those so far apart. Dispersion forces are present in all interactions between two molecules. And dipole-dipole is present here because of the polar moment. There is not hydrogen bonding. Hydrogen bonding is a special case if a hydrogen is bonded to oxygen, fluorine, or nitrogen. So that was not correct. This is a chlorine. So a lot of you described dispersion forces are present in all molecules, which isn't exactly right. They're present in all interactions between molecules. Based on temporary dipoles, temporary induced dipoles. So you explained that they were present, you got a point. If you described like why they exist because of the temporary induced dipole, you got a point. But the thing that a lot of people missed is that these intermolecular forces are literally the interactions between two different molecules as they approach one another and induce the dipole in one another. So I think that it's easy to think of dispersion forces as like a bond, but they're not a bond. And some of you didn't quite make the leap to describe like these are the forces that attract two molecules together. So if you didn't quite make that leap, I gave you 2 out of the 3 for that one. A lot more of you did do that with the dipole-dipole. These are permanent dipoles between two atoms with different electronegativity. So if you said dipole-dipole, you got a point. If you said this occurs when there's a permanent dipole between two atoms with different electronegativity, that's fine. And then the thing that it felt like a few people didn't quite take it to the final step, which is these are attractive to other molecules. Where the partial positive on one aligns with the partial negative on the other. So that's the thing that's like, be sure to take it to like the one next step is like, these are literally interactions between molecules that attract them to other molecules. I think that's where we go from having a polar bond to these being dipole-dipole intermolecular forces, is that they're between two molecules. So that's what I was looking for to get full points on this one. But on quizzes, I try to give a lot of partial credit. Okay, the next one, draw the following in bond line formula. So we have 1, 2, 3 carbons, and we know in bond line formula that I like to say each bend or end, each vertice or angle is a carbon. So I'm not going to draw the, draw a dot on there or whatever. I'm trying to make this line look thicker. But there is a carbon here, here, and here. So that represents my carbon 1, carbon 2, carbon 3, 1, 2, 3. And you assume that all the hydrogens that you would need to fill your octet are there. So And then you only have to draw in heteroatoms and any hydrogen that's bonded to a heteroatom. So you can draw the actual bond, or you can write OH. Either of those is correct. Or if you put the lone pair or not, that would be correct. So that's how you draw this molecule in bond line formula. And then the last one, the thing that a lot of people struggle with, but is probably the most integral to organic chemistry, is resonance structures. So, and the thing that I see a lot of students doing is trying to like go all at once for resonance structures, but it's important to go step by step. So resonance structures have a few rules. You can never move atoms, only electrons. And 2, it's best to start with areas of high electron density. So that would be lone pairs or double bonds or even triple bonds, but extra bonds. So I'm going to start here with these lone pairs, and I'm going to say that we could take this lone pair and move the electrons here. If we do that though, then there would be too many bonds to this carbon right here, and we don't want too many bonds to that carbon. So those electrons can only move there if we can somehow get rid of another bond, and we can get rid of that bond by moving these electrons here. So that would result in the Lewis structure that looks, or the bond line structure that looks like this. Now our lone pair has gone to this carbon right here. It still has its negative charge right there. Oh, actually, I'm not going to draw these around it because the proper way to draw your resonance structures is in a line like this with double curved arrows. So they're double-sided arrows. So, and I'm grading on this one for the drawing of the resonance structure and the every correct individual structure. So the curved arrows I'm looking for and the final product, not just can you get the final product and can you get the, but can you also get every individual step to get to these different resonance structures, because each one of these is a different structure that contributes to the overall hybrid. So then this would go here, and this would break, and we would get this structure. And these are all that I see. I don't see any other potential Lewis structures possible or resonance structures possible. And so in reality, this is what we started with. You know, the structure that looks something like this. But really, this structure is more like, let me see if I could do it justice. It's more like it has an area of high electron density here, and here, and here, everywhere that a negative bond shows up. And it's not really like it has an individual double bond on each one of these. It's kind of like these double bonds are shared between these two, because they go from, you know, here and here, these each have a double bond. And here, these each have a double bond. So it's kind of like they share the double bond. Like this lone pair is like shared kind of between this and this lone pair. I'll do that one in a different color. And these bonds are sort of shared between this. So you can kind of see, I guess this one, it would be more accurate to say this and this and not do that one. So you can kind of see like this is in reality more like what our hybrid of our overall molecule is, and that matters a lot when we start to get into more reactions, because the thing that's more negative will be more likely to form bonds if it has extra lone pairs. And so that's why we really focus in on on resonance structures so early on. And also part of why I made you draw this out and turn them in is because previously in the online class, we've had a lot of students who come into Organic Chemistry 2 where you have to draw curved arrows just constantly, and they're not really prepared for the class because they were able to not ever have to draw anything by hand and just answer the multiple choice questions. And so we decided to redo the online class and make it a requirement for you to have to draw things so that you can be adequately prepared. So I hope this was helpful. Let me know if you have any questions, and yeah.